Hello everyone, Assalamu alaikum. In this video, I will walk you through the memory management system I have implemented for KacchiOS, focusing on the memory.c and memory.h file. The goal was to design a simple memory manager for our operating system, supporting both stack and heap allocations. This is a fundamental part of any OS, as it allows dynamic memory uses for process and its kernel itself. So let's start with memory.h. Here I have defined the sizes for the stack and heap region. Uh, I introduce a structure called mem_block, which is used to manage blocks of memory in the heap. The header also declares functions for stack allocation and heap allocation also, freeing heap memory and initializing the memory manager. I implemented the stack allocator using a simple bump pointer in memory.h file. This means every stack allocation just move the pointer up and there's no freeing for stack memory. For the heap, this is the heap block. For the heap, I used a linked list of mem_block structure. Each block tracks its size whenever it's free to use and points to the next block. The heap allocator uses a first free strategy. It searches for the first free block large enough for the request, split it if necessary, and marks it as used. The heap free function marks a block as free and memory adjacent free blocks to reduce fragmentation. I also provide a memory init function to set up the heap. This is the memory init. Also memory init function to set up the heap when the OS starts. And for the integration and testing part, I include memory.h in kernel.c. Here is a kernel.c. I added test code to allocate memory. Here is a test code from both the stack and heap, free heap memory, and check if reallocation works. The result are printed in the serial console, confirming that the memory manager works as expected. Finally, I upload the make file. As the make file, I upload the make file to include memory.o, ensuring that memory.c is compiled and linked with the rest of the kernel. That's all from my side. Thank you all for listening.
Good afternoon, sir. I'm Don Mendita. For our group project KacchiOS, my responsibility was to build upon the initial memory foundation to implement deallocation, optimize allocation strategies, and that test the memory. For stack deallocation, I started with the stack. Our stack uses a bump pointer model. I implemented a LIFO deallocator. Since the stack pointer simply bumps up during allocation, my stack free function allows the kernel to pop the pointer back down. This ensures that temporary stack space is reclaimed immediately for the next set of operations. Now, for the heap deallocation, I implemented the code logic. When a pointer is freed, my code calculates the position of the mem_block header, which contains the metadata. By marking the free flag as active, the memory is returned to the available pool. Now, about now for the optimization, I implemented free list merging or coalescing to prevent memory from becoming shredded into tiny unusable pieces. I optimized it. It now performs immediate forward coalescing, merging adjacent free blocks in constant time. This keeps our linked list clean and ensures that small fragments are combined back into large, usable chunks automatically. I also to improve efficiency, I also optimized the heap allocation strategy. My friend originally implemented the first fit allocation, but then I optimized it for best fit algorithm. This logic scans the free list to find block that is the closest match to the requested size. This significantly reduces external fragmentation by leaving behind smaller fragments and preserving large contiguous blocks for future high demand requests. Now about stress testing. To prove the system is production ready, I developed a memory stress test. This function fills the heap, intentionally creates fragmentation by creating alternate blocks, and then verifies that my merging logic can successfully recover that space for a large 1024 byte allocation. This test confirms that our fragmentation handling and coalescing are working perfectly. Conclusion. By implementing these features, I've moved KacchiOS from a simple memory model to a more robust, optimized system capable. Thank you, sir. Thanks for watching.
Hello, my name is Najifa Fairujuthi. I have worked on process table. Here in this section, we have declared all the necessary libraries. Then we define the maximum number of process. And there is three states, free, ready, and current. We have defined the process control blocks with necessary functions. We have also defined the instance of process table and current process ID. And here in this section, there is all necessary function declaration. Here in this section, earlier we declared the structure of PCB and we have defined it right here. And for current PID, it keeps tracks of which process is currently running. If there is no process currently running, then it would be -1. And next, the static PID, next PID. This generates unique process ID, so no two processes share the same PID. And static PID 32 read head tracks the start of the ready queue for scheduling decision. Then the stack. And this stack sets a fixed stack size to simplify memory management. Then the enqueue ready function. This marks the process as ready and adds to the ready queue. Then get next ready function. This function returns the next ready process to be scheduled. Then next the init proc tab. This function initializes and clears the process table and global state. Next, the create process function. This creates a new process, allocates its stack, and makes it ready. This section of the course says the given process as the currently running process. Then the terminate process function. This function terminates a process and free its resources.
So I have built the process manager, I have worked on the utilities and the extensions of the function. Here I have built the utility functions where we can get the process ID from the process and also get the current process of the process running, and also some added some extra states like blocked and waiting. So here is my code, and I have firstly process.h, where I have declared some more states like PR block, PR waiting, and PR suspend. Also, I have added the IPC, where a sender can send a message to a receiver. Here we have a message type like sender PID, the data of the message, and the message length. Also, I have optimized the queue function, where the ready queue will be occurring. I have declared the head and tail of the queue, and after that also declared the queue type ready list, where the ready process will be held. And also I have added the queue functions like queue insert, queue remove, and queue empty to insert the processes in the queue. And for the utility functions, we have declared get PID to get the process ID, find slot to get the slots of the process, and then process state, process priority to get the process priority, is the process is valid, for that is valid PID, get stack base to get the stack address from the process, and the get num ready to get the process ready. Also, after that, we have the IPC functions like send and receive, which will send the message to the receiver. Also, the receiver can receive the message. Here we have two functions, send and receive. Now, let's go to the process.c, where we have worked on the queue operation. uh, Queue operations, if we have handled the range here, if the slot is less than 0 or greater than n proc, more than the process stack size, we will return the operating system. And then after that, we have also added the queue head and queue tail functions. And after that, we um, use the queue remove functions to remove declare the queue remove functions to remove the processes from the queue empty to empty the queue. And then we have in queue ready to insert the processes to the queue. Now I will be talking about the utility functions, where firstly we have a get PID, which will return the current PID, process ID of the current PID. And then we have a find slot options, which we will be using in our code and the scheduler code, where we will be getting the slot of the PID from the process table. Also, we can get the process state of the processes and of the processes. Also, we can get the process priority from the process with this function get process priority. And then if the process is valid or not, we can also get it from here. And the get stack base, get num ready here. And after that, we have also declared the functions of the inter-process communication, like sending the message or receiving the message. And then we have our send and receive function. And now we will be running test of our processes working fine or not. So for the process test, we have declared some tests in the kernel function. Let's check them. Here for test one, we have created some processes, and if the process ID is not declared, if the process ID is not there, then we will be passing the 0 and in the test 1 pass. And if all are okay, then test 1 is passed. Then test 2 pass, we are verifying the process states using the utility function, if the process state is in the ready state after creating the process. And after that, we have verified the process priorities, and if the process priority is 1, 2, or 3. If not, if, the process one is should have the priority of 1, then process 2 have the priority of 2, and the process 3 have the priority of 3. These are the tests. And after that, we have the ready queue count is okay or not. Then we have also verified the valid PIDs, like with this test. And after that, we have the trace test state transition test, where we have checked that the state changes with the process going through the current state. And then we have also seen the ready queue state transition after ready queue state transition. And after that, we have if the process is terminated successfully, we have also used some test cases for that. And we have also have the stack allocation. If the process is allocated in the proper stack in the memory, we have also test for that. And after those tests, if all tests are passed, then we can say that our process C and process H is running correctly. So let's run this. So we can see that our process tests are all passed, all tests passed of the process. And after that we have also some IPC tests where we have sent some messages to the receiver from the sender, and we can see that the IPC test also passed, like process creation of the IPC test, send message available or not, sender identification, message length, message content, and receive with sender check. This will all from me of the process C and process H. Thank you, everyone.
Assalamu alaikum sir, I'm Safiur Sifat, role 085. Today I will show you my process scheduler implementation for KacchiOS. I have implemented priority based scheduling, context switching in assembly, and configurable time quantums and aging mechanism. So let's dive in. The assignment required me to implement this. I implemented all this through three components: scheduler core, context switch, and process integration. At first, the heart of the scheduler is context switching. So I implemented here. You can see this is the assembly code that implements context switching. This saves all CPU registers of the current process, switches to the new process stack, and restores its register. That's how we have achieved multitasking. When creating a new process, we set up its stack to look like it already called yield. So the fast context switch just works. In the next file, scheduler.c, for scheduling policy, I implemented priority based round robin. In the code, you can see the schedule next function, schedule init, and reshed and yield, all the functions are implemented. This ensures high priority processes run fast within the same priority. It's fast come, fast served. The aging mechanism here prevents starvation. If a long priority process waits too long, we temporarily boost its priority so it gets CPU time. This is the aging code. We are having aging threshold, and if it exceeds that, we prioritize other process. So let me show it to you that it is working. If I use make run, you will see all processes are passed that fast. The process creation checks, tests are passed, then the inter-process communication, that's also passed, and then finally the scheduler code, it creates a process, then applies the aging and other mechanisms to implement to check priority based selection. And then we get a working shell, and the scheduler is fully functional. Then in the process.c, we have modified process.c to add these scheduling functionalities to processes. It allocates stack, initializes registers on stack, and set function pointers. Add to ready queue. The stack layout must match the what context switch expects when it pops registers. And that's my presentation. Thank you.